Okay, I've got a lot of slides to cover, almost 90 of them, so I'm going to go through a lot of them, early ones, pretty fast. A lot of you have already seen a lot of these photographs, but basically the surface stations project got started because I was looking at paint. I had an idea to do an experiment on paint, and we were looking at Stevenson screens, and we decided we had to make sure that the paint had been changed on the Stevenson screen. So the first one I visited was at the Chico University farm, and I found it right next to electronics, and I thought that was pretty odd since no one does that, puts heat-generating electronics next to the temperature sensor. They'd automated that Stevenson screen. Then I visited another one in Orland, California, and it was perfect. There were no problems at all, so I thought the first thing was a fluke. And then I visited Marysville, California, which of course has now become one of the most famous photographs of bad sighting examples out there, and discovered that its station was sited in the parking lot. I could stand there right next to those air conditioners and feel warm air blowing past me onto the sensor. And the fire chief parks his truck right next to the sensor there. So, when you look at the data between the two cities, and that's what we did right away, you realize, wait a minute, there's a difference. One of them is going up, and one of them is not going up so fast. What's the cause? Well, we figured sighting might be an issue. Got with Dr. Roger Pielke at the University of Colorado and started talking about it. Went out looking some more, found more stations with biases, such as the National Weather Service office in Monterey, California, sited right over Cinder Block, another station in Woodland, a regular co-op station measuring the temperature of a parking lot near the roof. Dr. Pielke and I decided to put together a volunteer program that you know now as surfacestations.org. We put together a website, solicited volunteers on blogs, and the project was on its way. These are examples of what we found. Some of you have seen a lot of these photos already, so I'm just going to step through them pretty quickly so I can get to the results of what we've done with the data analysis. We found all kinds of different surfaces that one would think that you just wouldn't want to put a sensor over, but in some places they really are more about aesthetics and making sure the grass doesn't grow under it so they don't have to maintain it than they are about worried about the measurement. About all kinds of different surfaces. The weed mat here and wood chips you'd think would be fairly cool, but when you walk on it you realize it's not so cool after all. This station here is not the original station, but is the one that got converted from it. We moved the MMTS up to the top of this tower here. We think the boat is there in the case of catastrophic sea level rise, but this is what the station really looked like when it was in operation through most of its life, but they had to move it because of vandalism. They couldn't keep people from damaging the station, so they moved it over here, and of course it got moved to what would you consider to be a warmer site. We found stations at sewage treatment plants like this one in Midland, Michigan, next to a vent for an underground tank that's blowing warm exhaust air out. The curator there says it never collects snow on the ground near the station during the winter. And we found them near sludge tanks at sewage treatment plants. We found them here in this nightmare of a sighting. This refrigeration unit was there. I called and asked, why is there a refrigeration unit in this area? And they said, because it gets so hot in this area when the workers are there doing maintenance that they have to have something to keep them from fainting. Seriously. We found them at sewage treatment plants where they've got incinerators and open sewage treatment pots right next to it. This one at Titusville, Florida, near Cape Canaveral. The MMTS is elevated and right next to the tank. When you look at sewage treatment plants with an infrared thermometer, you realize they generate a fair amount of heat. On the left, this photo here, taking invisible light, that's infrared. The air temperature was 0 degrees centigrade, and you can see that the temperature of the sewage treatment facility is significantly warmer. Does that have an effect? We think it does. We find them next to brick walls, which act as nice heat sinks for the sun. And we find them in people's backyard next to their swimming pool. This is a fellow in Livermore, California. That's a swimming pool there. You can see that it's darker. You can also see insulation on his house doesn't work so well. And even though he's got some great insulated windows there, the house is radiating heat. Oops, going backwards here. Excuse me. This one is in Perry, Oklahoma, near a fire station. You can see that it's right next to convenient parking right here, right on the street. This, I took a photo right after a rain. This is actually dark because it rained just minutes before I took this photo. And you can see even though the rain cooled down the area, there's still quite a bit of heat radiating from the surface there. We found these weather stations over concrete pads all over They want to keep things nice and neat, and they do a nice job of keeping things nice and neat. But that pad, of course, acts like a nice big heat sink, radiating its heat again at night. And that, of course, elevates the minimum and suppresses the variance of the whole signal. We found them at airports on the tarmac, strapped next to decks. We found them next to blowers. We found them over cinder, next to walls. We found them next to buildings. And even in the middle of the great state of Nebraska, where there's rolling prairies as far as the eye can see, where do they put the sensor? But right next to the building. We found them on rooftops. They did that because they wanted to keep it safe. We found it on this rooftop here in Roseburg, Oregon, right next to the air conditioning and all the other appliances up there. Santa Rosa, California, same kind of problem. On the rooftop, right in the middle of a giant heat sink next to air conditioning exhaust. It happens everywhere. This particular station in Baltimore was closed by the National Weather Service in 1999. It was downtown, right on the rooftop there. They closed it because they were getting temperatures that were not happening elsewhere. They had 13 maximas over 100 degrees where no other stations had any at all. And of course, that got left in the record. They didn't take those out of the record, but they did close the station. We found examples where they didn't get guidance from the Weather Service and people took things into their own hands. Well, I don't have a Stevenson screen. I'll make one. So here's one. Somebody put together out of bits and pieces of lumber and shutters and siding and all kinds of fun things. And this is what climate is being measured with in Cortland, New York. Found them next to air conditioners. We found them next to parking lots and air conditioners. There's where the old station was. Here's where the new station was, next to the parking and the heat exchanger there. We found a lot of building proximity issues. This one here is a famous photo because it prompted Steve McIntyre to start looking into what was going on with NASA in 2007. I had surmised that because there was a huge temperature spike at this particular station, it had to do with the proximity of the air conditioning vents. And we actually called and found out that, yes, indeed, they had swapped out the air conditioning units and placed them there, moved the station that very year where we saw the spike, and that's what we thought it was all about. It turned out that it was a splicing error on the part of NOAA, but the station helped bring that about. We found errors in sighting even at National Weather Service offices. This one here in Eureka is well shaded for at least half of the day. And we found them next to burn barrels and tennis courts. We found them in the middle of parking lots, like this one in Tucson, Arizona. And then there's this one, right over a gravestone. I thought when I saw this photo sent in to me by an observer, by one of our volunteers, I thought this had to be a joke. This had to be a Photoshop. This had to be, I mean, who would do this? And yet, after checking it out, it's real. There you go, right over a gravestone. And the Weather Service, where are they? We found them in parking lots, as I pointed out, and sometimes when they go into parking lots, things happen. This station in Lampasas, Texas, had a nice history, mostly rural, where it was had been placed before, but the observer was changed, and then when the observer was changed, they had to move the stations. They moved it downtown, right next to the highway and the parking lot there, and you can see what happened. And when you look at the difference between the homogenized data and the raw data, you see differences in trend lines. And so what this told us is that not only is the station move creating a spike, but the changes in the way that the data has been treated through the homogenization process is creating a false warming all by itself. Here's another example of a similar kind of thing. In Miami in Arizona, near a lot of very dark gravel right here, very high albedo, and you can see it from the air, and compared to the surrounding albedo, it's quite dark. You can imagine it picks up a lot of sunlight, converts it into heat. Well, here's what that station looked like. That's when it was moved. That's what its previous record was like. And again, after it goes through homogenization adjustment, the pass gets cooled, and we get the change in trend, partly due to that homogenization adjustment. NOAA's own adjustments themselves account for a significant portion of the warming in the whole USHCN data set. This is from USHCN 1. And even the new and improved USHCN2 has its own problem. When we compared some stations that used to be USHCN1 and then they got converted to the new USHCN2 algorithm, we saw the same thing happen again. We saw that the past got cooler and the trend went up. Here's another station, same kind of problem. The past was cooled, the trend increases. The message from all this, don't look at the homogenized data, analyze the raw data. So we've pretty well finished the surface station project. We're up to about 87% now. We got enough to get a signal. Earlier, we had people looking at it at 20%, 30%, 40%, where I'd shared some data. There just wasn't enough of a collection of stations to get a valid signal, mainly due to what's called the low-hanging fruit effect. We had a lot of volunteers doing this, but they would come from major cities and would often go drive to stations near them. So we had lots of clumps of cities, but we didn't have a good spatial coverage, like in the middle of the plains with a lot of rural stations. We got that filled in. And so now this is what the USHCN looks like with 87.4% surveyed. You can see the vast majority of them based on the siting criteria called the CRN system, which was borrowed from NOAA's own Climate Reference Network siting, shows that we've got a very, very large percentage of stations that don't meet the basic criteria. And these, of course, are the best stations right here, the CRN 1 and 2 siting criteria. So here's our qualitative conclusions from the project. 10% of the stations meet the basic 100-foot rule, or CRN 1 or 2. We found a lot of microsite biases and errors not being caught in USHCN and GISS, and adjustments to the station records are oftentimes increasing the warming trend. Here's some of the hypotheses we tested in analysis. I'm not going to spend a lot of time reading this because I want to get to the meat of all this and I'm running out of time. Okay, here's what we found in our analysis. Of the compliant stations, CRN 1 and 2, compared to the non-compliant stations, you can see that there's differences significantly between the T-min. The T-min is important. The T-min shows up more as a difference in stations than what we had expected, and we think a lot of that had to do with irrigation. Dr. Christie at the University of Alabama did a study in California in 2007 that showed that irrigation affected T-min significantly. And, of course, when you've got heat sinks like concrete, asphalt, and so forth near the sensors, you would tend to want to affect the T-min at night as it radiates the heat that it gathered during the day. We split the analysis into two parts, where we did 1979 to 1998, and then from 1998 to 2008. The reason is because we were in the middle of Pacific decadal oscillation changes and so forth. And so we had a warming trend followed by somewhat of a cooling trend. So we did two separate analyses. And so we split them up in such a way that we're able to look at these different year periods, these 10-year periods or so. And as you can see, this T-min trend holds, even though it's not as strong here, in this case where we look at MMTS stations versus CRS or the Stevenson screen stations. And then when you look at MMTS versus CRS stations, you see that the MMTSs tend to have much more of a warming trend at T-min at nighttime than the CRS or the Stevenson screen stations. We think this has to do with two factors, the irrigation issue, lawn sprinklers, that sort of thing, as well as the siting issue being closer to buildings and other heat radiating objects at night. A lot of it had to do with cabling issues. The MMTS is cabled, whereas the old station could be placed anywhere, and they couldn't get past certain barriers like sidewalks and driveways and so forth, because oftentimes the Weather Service didn't have the tools to trench. So when we compared CRS stations in the cooling period, 98 to 2008, again, we see the same kind of thing, but reversed. The T-min trends were higher for well-sited stations than non-compliant stations. T-max trends were higher for well-sited stations than poorly sited stations, but T-min was slightly lower. And then when we look at the MMTS stations, we find T-min, T-max, T-min trends were lower for well-sited stations. And then when you compare CRS to MMTS, overall, you see T-min cooled faster, then the CRS is the exact opposite that what we had during the warming trend. And this C-min team, excuse me, the CRS T-min trends were lower than MMTS trends. T-max trends were lower for MMTS stations than CRS stations. But T-min was higher, again suggesting irrigation, as noted by Christie 2007. CRS T-mean trends were lower than MMTS trends. T-max trends were lower for MMTS stations than CRS stations. Whoops, I'm reading the same slide again. Whoops. Let's see here, I must have made a mistake. Okay, here we go. All stations for the Stevenson screens. You can see that when we have the period 78 to 98, a warming trend, the differences were fairly great, and then the opposite slopes occur when we get during the cooling period. For the MMTSs, we had not quite so much of a slope. They seem to be fairly consistent with each other, but there's an offset associated with the other slope. Excuse me. So our findings are also based on urban versus rural stations. Now this is where it gets really interesting. We find that for the rural stations, these are lower in turns for the period than in urban stations, and this is not surprising. But again, when you look at the raw data, this shows up. If you look at the homogenized data, you don't find these things. For the 98 to 2008 period, urban versus rural stations, we find the reverse. T-min and T-max trends are highest for urban, lowest for rural. Urban and rural T-min trends higher than T-max. So the findings are, throughout both warming and cooling series, 78 to 2008, rural trends are considerably lower than urban. This is consistent with the hypothesis that urban heat has been increasing continually rather than remaining constant. If urban warming had remained a constant when trends went from warm to cool after 1998, there would have been a sharper cooling in urban areas than in rural. The fact that this did not occur post-1998, but instead urban cooling was less than rural cooling, clearly implies that there is a constant warming in urban areas. And here's what the graphics look like. And so the takeaway from this is that urbanization figures greatly into the placement of stations. Siting also matters. And that pretty well concludes. So what can we say? Our present surface measurements likely have been polluted by siting error, land use changes, and a gradual urbanization around the thermometers. Thank you very much.